So good morning, dear friends. So welcome you back to module 4 of fluid properties. So let me summarize what we discussed yesterday. So we discussed at length the property of viscosity, that is the resistance offered by the fluid particles to its free flow, the factors affecting viscosity, the units and dimensions of viscosity, that is the force units as well as mass units, and then we discussed the associated property called kinematic viscosity, its units and dimensions, and also we derived the Newton's law of viscosity and defined the various types of fluids, that is Newtonian fluids, non-Newtonian fluids, then plastic substance, and we also presented the rheological classification, that is in the form of a diagram in which the x-axis we represented the velocity gradient and the y-axis we represented the shear stress, and then showed the classification of fluids based on how they obey or do not obey the Newton's law of viscosity. So today we will work out a few numerical problems involving viscosity or kinematic viscosity. Now the example number is given in continuation of the previous examples. So two examples we worked out in involving mass density and specific weight and specific gravity. So now, let us go through the statement of the problem. A plate, so it is a flat plate assumed, 2 meters by 2 meters. So it has got a surface area which is a square, 0.25 millimeter distant apart from a fixed plate. So you have a stationary plate and then another plate at the top of it, which has got dimensions 2 meters by 2 meters and 0.25 meter distant from a fixed plate. Say for example, I have a bottom plate which is fixed. This is fixed, it's not moving, it's stationary, and I have another plate. So the vertical scale is blown up in order to have a visual observation. So this is the top plate which can move under the action of a shear force. So this the area is 2 meters by 2 meters surface area. It's a flat plate, and this distance, that is y, is equal to 0.25 millimeters. So the spacing between the bottom fixed plate and the upper moving plate is 0.25 millimeter. So this moves at a velocity of 40 centimeters per second and requires a force of 1 Newton. So the shear force to which the upper plate is subjected to is 1 Newton, and it moves at a velocity of 40 centimeters per second. So you are asked to find out the dynamic viscosity, that is mu, dynamic viscosity mu of the fluid in between the plates. So you have fluid in between these two plates, and I have to find out the viscosity of fluid. So let us use the Newton's law of viscosity, that is tau is equal to mu into dV by dy. So tau is the shear stress which is acting on the surface area of the moving plate. Mu is the viscosity which we have to find out, we have to determine, and dV over dy is the velocity gradient or the rate of angular deformation of the fluid. So we should know tau, we should know the velocity gradient in order to determine the viscosity of the fluid, which is filling the gap between the bottom fixed plate and the upper moving plate. Now tau is nothing but the shear force divided by the area over which the force is distributed. So this is given. this is 1 Newton, and area it is given, that is 2 meter by 2 meter square area, 4 meter square is the area of the surface of the plate. The distance between the fixed plate and the moving plate is 0.25 millimeter. So this we can express in meters, as because 1000 millimeters make 1 meter, and therefore 0.25 millimeter will be 0.25 into 10 raised power minus 3 meters. So velocity of the moving plate 40 centimeters per second, if you express it in meters per second. So we express all in SI units. So centimeters is in CGS system. So we will convert. So 100 centimeters make 1 meter, therefore 40 centimeters is 0.4 meter per second. And the force required to drag the plate at a velocity of 40 centimeters per second is given as 1 Newton. Okay. Now we are using Newton's law of viscosity, that is tau is equal to mu multiplied by dV over dy. Now we will assume that as the distance between the plates is very small, that is y is very small, we assume that the velocity gradient is linear, that is the variation is linear. So you have the bottom plate, the top plate, and then this variation is linear. So dV over dy can be replaced by v by y. Now v, we know that is so therefore mu is equal to tau divided by dV over dy. So tau is F by A, F over A. F is given 1 Newton, then area is 4 meter square, then the shear stress value is 0.25 Newton per meter square, and the velocity gradient dV over dy is v over y, that is 0.4 meter per second over 0.25 10 power minus 3 meters. This becomes 1600 per second, 1600 per second. So therefore mu is equal to tau divided by dV over dy. So you get 1.5625 into 10 raised power minus 4 Newton second per meter square. So Newton seconds per meter square is the force unit of viscosity. You can also express in mass unit as kilogram mass per meter second. You can also express like this, or kilogram mass per meter per second. Instead of Newton second per meter square, we can even use this unit. So let us go to the next problem, which involves kinematic viscosity. So at a certain point in oil, the fluid is oil, the shear stress is given, directly given. So tau is given. Tau is equal to 0.2 Newton per meter square. And the velocity gradient is 0.21 per second, that is dV by dy is equal to 0.21 per second. It's given. Mass density is given, that is rho is equal to 950 kilogram per meter cube. You are asked to find out the kinematic viscosity. So we know kinematic viscosity is equal to nu is equal to mu over rho. Nu is equal to mu over rho. So nu we have to determine, rho is given. So mu we should know. So mu we should find out. So how to find out mu? Mu you can find out using Newton's law of viscosity, that is tau is equal to mu multiplied by dV over dy. So tau is given straight away, 0.2 Newton per meter square. Mu is the unknown, and velocity gradient is given 0.21 per second. Therefore you can find out the dynamic viscosity as 0.95238 Newton second per meter square. So now as we know mu, we can find out kinematic viscosity as mu over rho. Rho is given, so 10 power minus 3 meter square per second. So we can also express kinematic viscosity in strokes. We know 1 stroke is equal to 1 centimeter square per second. So let us express 10 power minus 3 meter square per second in centimeter square per second. That will be, meter square means it is 100 square centimeter square. So this becomes 10 power minus 3 multiplied by 100 square centimeter square per second, which comes to 10 stokes. So we have kinematic viscosity as 10 stokes, or you can just leave at this level as 10 power minus 3 meter square per second. Suppose if the answer is asked in stokes, you have to convert this meter square per second to stokes like this. I hope you have understood the conversion. Now, example 5, the next example, the third example under viscosity, the equation of a velocity profile over a plate. Now here the velocity profile is not linear. So it is say following a second degree curve like this. V is equal to 5y square plus y, where V is the velocity in meters per second and y is the distance from the bottom plate. Say this bottom plate is fixed, this is fixed plate, this is the moving plate. So at any distance y from the bottom plate, the velocity is v, say the velocity is v. So you are asked to find out the shear stress at y is equal to 0. That means here y is equal to 0, that is at the top of the fixed plate, and y is equal to 7.5 centimeters, that is above the bottom plate. So the viscosity of the liquid is given in poise, 8.35 poise. So the velocity profile is not linear, it is non-linear. It is non-linear. It is a second degree equation. Something like a parabola, right? So this poise, let us convert into fundamental SI units. One poise is 0.1 Newton second per meter square. So 8.35 poise makes 8.35 multiplied by 0.1 Newton second per meter square. That is 0.835 Newton second per meter square. Now you are asked to find out the shear stress tau at y is equal to 0, that is at the bottom of the fixed plate, and at y is equal to 7.5 centimeters, that is 7.5 centimeters from the fixed plate. So the velocity profile is given as 5y square plus y. Now, as per Newton's law of viscosity, tau is equal to mu multiplied by dV over dy. So we have to get the quantity dV over dy. That is, I have to differentiate this expression, that is, you have to differentiate the function for v, that is d by dy of 5y square plus y. Now this can be written as d by dy of 5y square plus d by dy of y. So 5 is a constant, it can be taken out. So this is 5 into 2y. So d by dy of y square will be 2y plus d by dy of y will be 1. So I have 10y plus 1. This is dv over dy. This is very ordinary differentiation. So I get 10y plus 1. That's a velocity gradient. So shear stress as given by Newton's law of viscosity, tau is equal to mu dv by dy. At y is equal to 0, the shear stress, that is tau at y is equal to 0, is mu multiplied by, mu is a constant, the dynamic viscosity is a constant for the fluid, at y is equal to 0. That means dV by dy at y is equal to 0 means you put y is equal to 0. So 10 multiplied by 0 plus 1. So 0 plus 1, 1 per second. Therefore, tau at y is equal to 0 will be 0.835 Newton second per meter square is the viscosity, multiplied by 1 per second you get 0.835 Newton per meter square. This is the shear stress at the surface of the bottom plate, which is fixed. Now at y is equal to 7.5 centimeters, that means 0.075 meter, because 1 centimeter is 10 power minus 2 meter. That is 100 centimeters make 1 meter. So 1 centimeter will be 10 power minus 2 meter. So 0.075 meter. So shear stress tau at y is equal to 0.075 meter is mu multiplied by dV over dy, that is velocity gradient at y is equal to 7.5 centimeters from the bottom plate. So that becomes, you put y is equal to 0.75 meter. So 10 multiplied by 0.75 meter plus 1, you get 1.75 per second as the velocity gradient at 7.5 centimeters from the bottom plate. So you get 0.835 Newton second per meter square multiplied by 1.75 per second, you get the shear stress as 1.461 Newton per meter square. So at the bottom plate, at the fixed plate, the shear stress is less, whereas at 7.5 centimeters from the bottom plate, the shear stress is high because the velocity gradient is high. So let us take the next example. As shown in figure below, this is the figure that is given in the problem. A cubical block of 20 centimeter side. So it's a cubical block. So of side 20 centimeters. Each side is 20 centimeters. And of 20 kilogram weight. So what is the weight? 20 kilograms. See, please note, when I say weight, it is a force quantity. So this is given in MKS system. So you have to convert into SI system. That means you have to multiply by 20 kilogram force multiplied by 9.81 Newton per 1 kilogram force. So this you get the weight in newtons. So 1 kgf is equal to 9.81 Newton. Okay. So that is 196.2 newtons weight of the cubical block. And it is allowed to slide down along a plane surface which is inclined at 30 degrees to the horizontal. So this is the horizontal. And this is the inclined plane. Which is inclined at 30 degrees to the horizontal. And in between the plate, the bottom surface of the block and the plane, you have a fluid which has got a viscosity. This is the fluid which has got a viscosity 2.16 into 10 power minus 3 Newton second per meter square. So what will be the terminal velocity of the block if the film thickness? So this thickness, the film thickness is also given. This thickness is also given, that is y is given. Y is equal to 0.025 millimeter. You are asked to find out the terminal velocity if the film thickness is so much. So now this is, I have given the free body diagram of the given problem statement. So this is the center of gravity of the cubical block, which is sliding down the inclined plane. This is the horizontal, this is the inclined plane. This is the inclined plane and this is the horizontal. The cubical block is sliding down the inclined plane and this is the center of gravity. Now there are two forces acting on the system. One is the self weight of the block, that is W, which is acting in the vertical downward direction. So W acts in the vertical downward direction through the center of gravity of the block. Then you have the shear force or the drag force, which is responsible for the sliding of the block down the inclined plane. Now this force is acting parallel to the inclined surface. So these two are the forces which you have to consider for the equilibrium of the block. When the block is just to move, right? Say when it is in equilibrium, you have sigma F, that is the algebraic sum of forces in the system should be equal to 0. Now how to find out the force F in terms of the self weight of the block? Now I can resolve this self weight. Say the self weight is acting vertically down, whose value is known. Now this is the direction in which the block slides, and this angle, that is this angle is 30 degrees. This angle is 30 degrees. This is given 30 degrees and therefore this will be 30 degrees. This angle will be 30 degrees. So how? Now if you take this will be 90 degrees, this will be 60 degrees from this right angle triangle, and this will be 60 degrees, this is 90 degrees, and therefore this will be 30 degrees. This is 30 degrees, this will be 90 degrees, so this will be 60 degrees from this right angle triangle. So opposite angles will be equal. So if you take this triangle, right angle triangle, this is 60 degrees, this is 90 degrees, and therefore this will be 30 degrees. Now the component of W, this is W can suppose if you take W as a resultant, it can be resolved into two components, mutually perpendicular components, one in this direction, that is perpendicular to the inclined surface, and another along the direction of the movement of the block. So this will be, so this is 30 degrees, this will be 60 degrees. So this is W, this is F, and maybe you can shift this component will be F is equal to W cos 60, or you can also write as W sin 30. This is 30 degrees, this is 60 degrees. So the component of W in this direction is W cos 60, or it can be W sin 30. So you get the F value. So now you can find out the shear stress. So F is 98.1 Newton and area, that is 20 centimeter side. So 20 centimeter by 20 centimeter. That is the bottom area of the block in contact with the inclined surface. So this is 400 centimeter square. This will be 400 into 4000. 400 centimeter square, which will be 400 into 10 power minus 4 meter square. So you get 0.04 meter square, because 1 centimeter square is equal to 10 power minus 4 meter square. So 0.04 meter square is the area. So you get the shear stress that is developed at the bottom of the plate is 2452.5 Newton per meter square. So again we will use Newton's law of viscosity. Tau is equal to mu multiplied by the velocity gradient dV over dy. So again we assume that as the distance between the inclined plane and the bottom face of the sliding cubical block is very small, so 0.025 millimeter, the variation in velocity from the inclined plane to the bottom face of the moving block can be assumed to be linear. Hence, we can replace dV over dy by V by y. So, therefore, the above equation becomes tau is equal to mu in multiplied by V over y. So, tau we have just now determined. Mu is given in the problem, 2.16 multiplied by 10 power minus 3 Newton second per meter square. This is what the terminal velocity what we require, and the distance between the bottom surface of the cubical block and the inclined plane surface is 0.025 into 10 power minus 3 meter. So from this, if you simplify, you get V is equal to 28.3 meters per second. So V will be equal to this much. I hope you have understood the concepts and the details given, explained in the 4 examples we have seen. Applying Newton's law of viscosity and also assuming linear variation of the velocity gradient as the distance involved between the plate or the block which is moving and the surface on which it is moving is very, very less. So with this we come to the conclusion of module 4, and again in module 5 we will work out some more problems on viscosity, and then we will move on to the next property in module 6, that is vapor pressure. So with this, thank you very much for the patient hearing and listening. Thank you so much, and have a good day.